Hey guys, so question 7 is asking us to predict the product of the following reaction. And so what we need to recognize here is that we're performing the bromination of a compound, and so that's given away by having that dibromo compound as well as the UV light. The UV light is very important because that's what's going to allow us to perform our first initiation step, which is going to turn that dibromine compound, regularly just referred to as bromine, that's going to give us a product when we have the UV light of two radical bromines. Now those radicals are important because in bromination and chlorination, what's going on is we have propagation steps that involve these radicals, and so that first one of these bromine radicals is going to be attacking the hydrogen on whatever is the most stable location. In the case of bromine, chlorine, the other compound that you would use these radical reactions with, that is not going to be selective like bromine. And so in this product, we're going to want to find the most stable location where we can put that bromine. Whereas if we were doing chlorination, we'd have we'd have definitely more than one product. And in this case, we'll also have more than one product, but we'll have a major product, and that's going to be the most stable product, whereas chlorine isn't so selective. And so just all in all, bromine, you want to find your most stable location. Chlorine, you're going to have some different varieties of products. Okay, so now let's go ahead and take a look at just our stability, just for a refresher. We've got primary is the least stable in comparison to secondary, tertiary, allylic, and benzylic. Primary would just be a carbon that is attached to one other carbon. Secondary would be a carbon that's attached to two other carbons. I think you get the idea for tertiary. Allylic is going to be this position here that is next to a double bond. So notice that it's not on the double bond, it's next to the double bond. And so that would be the allylic position, and that is more stable than primary, secondary, and tertiary. And then a benzylic position, that would be when you have the benzene ring. And again, it's not on the benzene ring, but it's on the carbon next to the benzene ring. So it's not on the benzene ring itself anywhere, it's on the carbon next to it. Benzylic bromination, where we actually put the bromine on the benzene ring, that's going to be requiring a much different set of reagents, not UV light bromine. It's going to require its own set of reagents, and you won't get to that until OChem 2. And then allylic bromination, we're actually going to go a little bit more in depth on allylic bromination at the end of this video, because that is also something that requires its own reagents. But we can get a benzylic here, the benzylic position. We are able to get that product just using bromine, dibromo compound, and UV light. Okay, so if we're taking a look at this question directly, it wants us to predict the product of the following reaction. And so what we're going to look for bromine in particular is we're going to look for the most stable location that we could put this bromine on. And so let's look at all of our carbons. We've got 6 carbons that are on the benzene ring, and we just went over how we're not going to put that there for right now. You just walk away. Just walk away from any benzene. You're not going to put anything on there. In OChem 2, you'll figure out how to do that. But for right now, you just walk away. Okay, so then we've got 3 other carbons besides those. We've got this carbon, and this carbon. Okay, and so let's go ahead and label those carbons. Let's start here over on the right side. So this would be a primary carbon because it's only attached to one other carbon. This would be a secondary carbon because it's attached to this carbon here and this carbon here. And then this, you might want to say that that's a secondary carbon, and technically it is, but it's right next to a benzene. It's a carbon that's right next to a benzene, so we call that a benzylic carbon. And so that would be our most stable location. And so when we decide what our product is going to be for this reaction, we would actually choose here on the benzene, and then I'm not going to fit it in that little box. So on this phenylpropane, we would add a bromine here at this location. And so we're just going to double check to see that we fit this molecular formula here. And we've got 6 carbons, 7, 8, 9, looking good. The hydrogens, there's going to be one here, one here, one here, one here, one here. That's 5. There's no carbons here because this has a double bond right here. So no carbons there. Hydrogens, I'm sorry, no hydrogens there. We've got a hydrogen here, 2 hydrogens here, and then 3 hydrogens here. So all in all, that adds up to the 11 carbons that we need. It's looking good. And then we've got the 1 bromine. So that all fits the molecular formula, so that would be our correct answer. And so that's a pretty straightforward question, honestly. You just look for the most stable position and put it right on there. If this was chlorination, you would get different positions. You'd get the benzylic secondary and the primary, and you get that in different ratios, but bromine is very selective with a ratio of 97 to 3, whereas chlorination you have, like, let's say 50, 60, 50, 40, 10. So bromine, very selective. Okay, that's the real takeaway here. And in case you get a problem like this where it gives you the starting compound and it gives you the product, it might ask you what's the reagent here that will make that happen. That's a common question that he might throw at you. And so for that, you're going to want to actually fill in this bromination and UV light, or if it's a chlorine, you want to do chlorine and UV light. But make sure that you include that UV light. It's very important because that's what's going to let our initiation step occur. Okay, and then I just want to talk really quickly about allylic benzene, allylic bromination. The reason I want to talk about it is because a lot of people will want to put a bromine here instead of, like, let's say here, because this location we know is more stable than a primary carbon. However, we actually would not put a bromine there if we were doing a bromination with UV light. I'm going to make this a little smaller. So this is pretty important. So if we were doing a bromination of this compound here, which would be a butene, if we were doing the bromination of butene, one might be tempted to put the bromine here at the allylic position, but the product in this case would end up being a dibromo compound. So you'd get a vicinal bromination from that, vicinal meaning neighbors. And so you wouldn't get the 1 bromine attached onto this compound. And that's because allylic bromination, putting a compound specifically on an allylic carbon, requires a very specific reagent, and that's NBS, N-bromosuccinimide. You guys will learn about that later in the future in OChem 2, most likely. But that would be the actual reagent that would give us this product here, this bromination. And so just if you come across that and you're wondering, okay, well, where do I put, if you come across this with a double bond and you're doing the bromination with a dibromo compound and UV light, you'd actually get vicinal bromides instead of putting only 1 bromine on there. So hopefully that makes sense. That's some more in the future kind of stuff, but it is important to mention because it's something that you could see on your assessment, especially considering right now that you're looking at bromination and chlorination. So what I suggest you do is you go on to masterynorganicchemistry.com. It's a fabulous site. Look up allylic bromination and it will explain why it is that you need to use a specific compound for allylic bromination in comparison to primary, secondary, tertiary, and benzylic.